almost all of these reactions, the reactivity of the nucleophile is going to play an important role, as well as the base strength. So let's first take a look here at some of the factors that affect the strength of a nucleophile. The first thing that I want to look at with you is what happens when we go across a row of the periodic table. So remember, as we go up the periodic table and as we go to the right of our periodic table, we have an increase in electronegativity. Okay, I'm going to come back to that in just a second. And what I want to look at with you guys right now is this. So here we're going from HF to H2O to NH3 to CH4. So what's happening is we're breaking a bond here from H to F. So there's an H to F bond that's broken here. Or an H to an OH, right? Or an H to an NH2, or an H to a CH3. Right now, when we look at the periodic table, right, we have fluorine, oxygen, nitrogen, carbon, right? So as we go over here to the right, we become more electronegative, right? So with CH4, when we lose this H that's here, we become CH3 with a lone pair and a minus. Right? NH3 becomes NH2 minus. Of course, water becomes hydroxide, right? And then HF becomes F minus there, right? So the idea here is we go across this and look at our basicity. So you go from 50 for your pKa, 35, 15, and 3.2. Right? So a pKa of 50 is a very weak acid. So very weak acids make very strong conjugate bases. Now the idea here is that the more electronegative atom, right, the more tightly the electrons are held onto. This results in a decreased lone pair availability, and that decreases nucleophilicity. So again, across a row of the periodic table, the nucleophilicity, it parallels basicity. So stronger bases are stronger nucleophiles here. So across a row here, CH3 minus, that carb anion, is a stronger nucleophile than F minus. So just think of F minus, it's really holding on tightly to those electrons since it's the most electronegative across that row, and it's less willing to give them up to make a bond to a carbon atom. So in acid-base pairs, the trend in nucleophilicity, it matches that of basicity. So a base is a stronger nucleophile than its conjugate acid. That's an easy thing to say. So what does that mean, right? So here is an acid, right? And here is the base that gives rise to. So that base is a stronger nucleophile than its conjugate acid, right? So here is a base. If we throw a proton on there, you get NH3. But that NH2 right there is a stronger nucleophile than this uncharged NH3 or H2O. Well, what about size and polarizability? Well, that matters too. So it turns out as an atom increases in its size, the electron cloud becomes more easily deformable. And remember, that ability of that electron cloud to become deformed is called polarizability. So as a consequence, larger atoms have a higher polarizability. They can make a bond easier and they're more reactive. So as we talk about size, we're really going up and down a column of the periodic table, right? So larger atoms, iodide larger, fluoride smaller, better nucleophile for iodide, right? So the idea here, if we look down here below, here's fluoride. We might say that has a hard shell, right? A small valence shell is another way this is sometimes put. And in one of the reactions that we're going to see, the fluoride would actually have to come over here and approach and overlap with this this particular orbital. It's the sigma star antibonding molecular orbital. Now, we're not going to get into this a whole bunch when we look at the reaction, but that overlap needs to occur. Right, so it approaches here, and there's little bonding that occurs as we approach. We have to get really close in. However, down here with iodide, you have this large shell. Right, you can see it looks like it's a little bit more diffuse or a little bit more easily deformable because of that gradient that you see there and the intensity of the blue. We say sometimes this has a soft shell or a large valence shell. And again, we still have that sigma star antibonding molecular orbital. And then this guy also needs to come in and overlap. But because the electron cloud is more deformable, we end up getting this more bonding kind of interface as we get closer. And these are our transition states, right, for this reaction. Okay. So again, just to summarize here, larger atoms, better nucleophiles than smaller atoms. That's the other trend to look at. Now, steric size matters too. So remember, the nucleophile has to come in and physically touch another atom. So the more steric hindrance that we have around that nucleophilic atom, the more hindrance we have towards that nucleophile being inefficient or a good nucleophile. So here's an example. This oxygen with a minus charge, that's your nucleophile end, right? Here we have 1, 2, 3, right? CH3s on that. And these are large, so I'm representing them over here with these big kind of spheres, essentially, okay? Now, because we have this large part of the molecule here, that's going to interfere with that oxygen, right? If you look back up here, for example, in this reaction, that oxygen would have to come over here and physically touch right there. So if there's a bunch of junk around it, then it just inhibits that in this case, backside attack. Here we have our little group, our CH2 group, our carbons. These are just kind of stuck straight out. So it's more like a spear. It can come in and it can approach that angle a little bit better. This is ethoxide. It's a weaker unhindered base. It's a stronger nucleophile though. Now solvents are also going to affect the ability of our nucleophile to make a bond with a carbon atom. So there's two types of solvents. One is called polar protic solvents, and the other is polar aprotic solvents. So a lot of these reactions involve ions to some regard, and we have to use a solvent in which all of the reactants are soluble. So we're going to pretty much have some type of a polar solvent. Right, so if it's nonpolar, then you don't get things dissolving well, right? Now, polar protic solvents, just like the name implies, it's a polar solvent, and protic for us means that we have an OH or an NH. So it's like water or an alcohol or an amine or something along those lines. They tend to reduce the strength of the nucleophile. And it turns out that nucleophiles are going to be solvated, and more importantly, small nucleophiles get solvated more easily. So if you're solvated, right, like if you're fluoride and you want to come over and you want to make a bond here, in this little picture that I made, if you want to come over here and do this and make a connection to that carbon, then you actually have to strip away and move some of that solvent out of the way. And that costs energy. So we have to move that stuff out of the way, and once we've desolvated this enough, then we can kind of come in and we can, right, attempt to make a bond with our carbon, and we get like this nice little transition state here where we're making a bond with that carbon atom. So again, it's kind of like, fluoride, it's like this little marble that's inside of, this solvent shell of like a soccer ball or something like that. And before it reacts, we have to kind of open up the curtains around that soccer ball to expose fluoride so it can physically touch the carbon atom. So remember, smaller nucleophiles, they get solvated more easily. Larger ones, because they're more polarizable, the solvent can kind of move out of the way a little bit easier. And the other thing to point out here too is that polar protic solvents, they're going to solvate both the cation and the anions. So our anions are basically going to be our nucleophiles. So we don't really, if we want them to react fast, then we'd like them to not really be solvated. And that's what we solve in using this second solvent down here. Now this is a polar aprotic solvent. Now all this means is that we have a solvent with no OHs or no NHs. And because of that, we don't hydrogen bond with the nucleophile. And because of that, those nucleophile anions, they don't get solvated and therefore are more reactive because they're just more available for making a bond to that carbon atom, right? So some common types of aprotic solvents down here, acetonitrile is one, DMF, another one, acetone, right? One of another choice here. And there's lots of other ones, but this covers the basics for this chapter. Right, so if you have, for example, sodium X minus, and here's your halide, right? That would be your nucleophile then, right? And if you put that in acetone, it turns out that this cation, sodium, gets solvated. And that's solvated by the oxygen atoms that have a delta minus on them, right? For your partial charge because of that dipole. But the anions are not well solvated. So they end up being a little bit more free. And if you're more free, then you're more available to simply react.